The goal of this video is to list and justify three important properties of lower and upper sums. First, a quick reminder of the definitions. I will be talking about a bounded function f defined on a closed interval a, b. I won't be repeating this all the time. Here is the graph of the function. I take a partition P of the interval. The P lower sum of f is the sum of the areas of the rectangles below the graph of f, in red in the picture, and the P upper sum of f is the sum of the areas of the rectangles above the graph of f, in green in the picture. Notice that a lower or an upper sum depends on three things: the function, the interval, and the partition. More precisely, here is the actual definition. I assume this is all known. If it isn't, or if it went too fast, I invite you to re-watch the video with the definition of integral, link in the description, where I explained all of this much slower. The purpose of this video is to present three important properties of lower and upper sums, including one property I left pending in the previous video. These three properties will make some calculations and some proofs easier. Let's start with an easy one. For any one partition, the lower sum is smaller than or equal to the upper sum. This seems clear geometrically. If I am fixing a single partition, then the area of the lower rectangles is less than or equal to the area of the upper rectangles. Why? Focus on one single subinterval. The lower rectangle is literally contained in the upper rectangle. The height of the lower rectangle is the infimum of the function in that subinterval, and the height of the upper rectangle is the supremum of the function on that subinterval. The infimum is always less than or equal to the supremum, and therefore the sum of the areas of the lower rectangles is less than or equal to the sum of the areas of the upper rectangles, which is what I wanted to show, nothing mysterious here. Let's try something more interesting. Can we compare lower and upper sums for different partitions? And what makes one partition better than another partition? There is a sense in which some partitions are better than others because their lower and upper sums will be better estimates for the integral. Naively, it looks like a partition that has more points will be better, but it is not merely about the number of points. Here is a new definition. Given two partitions P and Q, I am going to say that Q is finer than P when P is a subset of Q. For example, this partition Q is finer than this partition P. It means that Q has all the points in P plus a few more. It does not mean merely that Q has more points than P. How does this help? Let's see what happens when I add one single extra point to a partition. Begin with this partition P with 5 points, 4 subintervals. I am shading the area of the lower rectangles for the lower sum. Now let's add one single extra point, which I will call T. This extra point breaks one subinterval into two and creates one extra slice. And what happens to the area of the lower rectangle? It increases a bit. This will always happen when I add one extra point. The lower sum will increase or stay the same. And if I add a few points, one at a time, the same thing happens as well. We have found the second important property. Let P and Q be two partitions of AB. If Q is finer than P, then Q produces a better lower sum than P. A better lower sum is a larger lower sum. And also Q produces a better upper sum than P. A better upper sum is a smaller upper sum. I have explained why this is the case for lower sums only, but I trust you can repeat the same reasoning for the upper sums. This is helpful when one partition is finer than the other. But what if I have two partitions and none of them is finer than the other? Can I still compare their lower and upper sums? In general, without knowing anything else, I cannot compare the two lower sums and I cannot compare the two upper sums, but I can always say that every lower sum is less than or equal to every upper sum. This is going to be the third property. If I take any two partitions P and Q, without knowing anything else, I can guarantee that the P lower sum is less than or equal to the Q upper sum. In other words, every lower sum is less than or equal to every upper sum. If you try to prove this algebraically by setting two arbitrary partitions, it looks messy. I would not know how to start. But there is a clever trick to make this into a very simple proof. Here it is. I know how to compare lower and upper sums between two partitions when one is finer than the other. So let's define a third partition that is finer than both. Let us call R the union of P and Q. R is a new partition. R is finer than P and R is finer than Q. And then look at what happens. The P lower sum is less than or equal to the R lower sum thanks to property 2, which is less than or equal to the R upper sum thanks to property 1, which is less than or equal to the Q upper sum thanks to property 2. And that completes the proof. There we have it. These are the three important properties of lower and upper sums. They come in handy in various situations. In particular, I had assumed property 3 when I define integral, in order to conclude that the lower integral of a function is always less than or equal to its upper integral. A good way to summarize and to remember the three properties is with this picture, which I had already used in a previous video. By now, the picture is fully justified.